Okay, so now we're pretty deep into chapter 1. We've just finished talking about equalities. Now we can start to think about using those equalities, whether we're talking about metric system relationships, as we did in the last lecture, or really any equality as a conversion factor. So a conversion factor just allows us to go from one unit type to another, or one particular, when we get into chemical reactions, one particular reactant or product to another. So it's a very important skill for the course, and it's something that if it's not coming naturally to you, you really need to reach out for help sooner rather than later, because it doesn't go away, and it is probably one of the more important skills you learn in the course. So just as we described in the last lecture on equalities within the metric system, any equality uses two different units to describe the same measured amount. So these could be between units of metric system, across the US units, which is officially called the English system, even though the English use metric, and between metric and English units. So we could have, say, 10 millimeters equals 1 centimeter. That's within the metric system. We could have 1 foot equals 12 inches within the US units, or we could have 1 inch equals 2.54 centimeters as examples of length measurements. We also see some other examples here with 1 meter equaling 1,000 millimeters, again within the metric system. 1 pound equals 16 ounces within the US or the English system, and then 2.20 pounds equals 1 kilogram. There we have across the metric to the English or US units. Within a system, I would expect you to be able to come up with the equality yourself. Across systems, like that last example, when we're comparing English or US units with metric units, I would provide that conversion factor. Now, you may have your own method already, and as long as you're comfortable with it and it always works, that's fine. But if this is new to you, or if you're not having a successful try with your current system, I would advise you to write these equalities as a fraction, right? Anything divided by itself is 1. So if we look down at the example, 60 minutes over 1 hour, well, 60 minutes is exactly equal to 1 hour. So that relationship there, that fraction, is equal to 1. And when we multiply by 1, we don't change anything. Of course, it doesn't look like 1. It looks like 60 over 1, but again, with the units there to make it an equality, we're justified in making that conversion factor. And so again, because it's a conversion factor, because they're equal, it doesn't matter which is in the numerator and which is in the denominator. We could have 60 minutes over 1 hour, or we could have 1 hour over 60 minutes. Either way, since those are equal, it will give you 1 overall, and therefore not change things numerically in terms of doing bad math. It's all legitimate, it's all allowed. But sometimes, based on the problem that we're solving, we may need minutes in the denominator to cancel with minutes earlier on in the numerator someplace, or we may need the reverse, hours in the denominator to cancel with hours earlier in the problem. Here we see table 1.11, where we have just a number of different common equalities, and obviously within the systems, hopefully you're getting used to these prefixes and the metric system being based on powers of 10. It's a very logical system, and as long as you know your prefixes, you shouldn't have any trouble. US units, you may know some from your use of that system here in the United States, but I would ordinarily provide those just because they're not always common knowledge anymore. And then finally, that last column with metric to US, of course, I've already promised to provide those values if we decided to have problems like that come exam time. Of course, for homework sets, you can look it all up. Just go to table 1.11 in your text or review this slide. But on the exam, with it being closed book, closed notes, I would provide those values just for the metric US, not the metric itself. Now, just one more distinction. Of course, when we're within the metric system or within the English system, when we say, for instance, that 1 centimeter equals 10 millimeters, that 1 and that 10 are both exact numbers. They're infinitely significant. They don't affect your significant figures. Likewise, saying that 1 foot equals 12 inches, that 1 and that 12 within the US system would be exact numbers, not subject to sig fig rules. When we go across systems, when we have the metric in the US examples like 2.54 centimeters equals 1 inch, those are actually measured numbers because we're trying as best as possible to relate these two dissimilar systems. So those do apply sig fig rules, and it does matter. So aside from that one that I happen to mention, the 2.54 centimeters equals 1 inch, we assume that 1 to be exact, that 2.54 to be exact. When we say 2.20 pounds equals 1 kilogram, well, if we just say 1 kilogram, that's 1 sig fig. So ordinarily we might say something like 1.0 or 1.00 kilograms in that example if we are concerned with significant figures. So just be careful within a system. We assume it to be infinitely significant across systems, aside from that 2.54 centimeters equals 1 inch exception. Across US and metric systems, we do consider those to be significant figures, and sig fig rules will apply. So like we discussed earlier, we can take that equality, in this example a metric equality of 1 meter equals 100 centimeters, and we can go ahead and write that as a conversion factor, as a fraction with either the 100 centimeters in the numerator and the 1 meter in the denominator, or with the 1 meter in the numerator and the 100 centimeters in the denominator. It's really going to be the problem that determines which way we represent it, because at the end we're going to want to cancel all the units that need to cancel and be left with the unit or units that we want for our final answer. Here we see some of those equalities across systems. So 2.20 pounds equals 1 kilogram. Of course, we could represent either in the numerator and the denominator. However, we need it for the problem that's at hand. But that 1 kilogram is exact. The 2.20 pounds is measured. So that's 3 sig figs. Ordinarily, to make it clear, I would also put, say, 1.00 for the kilograms. So just to make it very clear, but it's understood whenever we say 1 of something, we mean exactly 1. Likewise, with the 1 quart equals 946 milliliters, we expect that the 1 quart is exact, but the 946 milliliters is a measured number, so therefore 3 significant figures. But again, I would ordinarily write 1.00 quarts, for instance, so that you're not confused by that subtlety, but you may see it out there, or certainly the problems in the text may expect you to know that that 1 quart or 1 kilogram in these examples is an exact number. Okay, if we think about equalities on food labels, we'll often see both metric and US units, and that's not just hopefully to prod us to start thinking metric, which is a nice effect, but obviously it's more important that you have both unit types represented if you're going to sell your product in multiple countries. If you're going to market your product in the US and Canada, or the US and Mexico, for instance, our neighbors there, it's important to have both systems, because either of those neighbors will be expecting metric things like grams, whereas in the US we'd expect things like pounds and ounces, because that's what we're used to. So that's another neat way in everyday life to start getting these relationships down. If you're looking at your food labels and seeing the ounce to gram conversion, hopefully it becomes a little more real, and hopefully you'll all start thinking a little more metric, not only in chemistry class, but also in everyday life. Alright, so let's pause a moment for a learning check on this topic, and let's see how you do with writing the equalities and then the conversion factors for these problems. So number 1, liters and milliliters. So write the relationship that is the equality, how many liters equals how many milliliters, and then the conversion factors where you have milliliters and liters, 1 in the numerator, 1 in the denominator, and then the inverse. Same thing for hours and minutes, and then finally meters and kilometers. So take a moment and jot those down. Pause the video if you must. Otherwise, let's take a peek and see how you did. Okay, so hopefully that was a pretty easy exercise. So obviously I went with the more standard here, but instead of 1 liter equals 1,000 milliliters, you could have had 0.001 liter equals 1 milliliter. Students tend to think about it this way, but that's another equally valid equality, so just be careful. You could do it multiple ways that it may still be correct. And then finally, if you did it this way, the 1 liter over the 1,000 milliliters, or inverse actually, the 1,000 milliliters divided by the 1 liter. Either one is acceptable, depends on the problem. And then finally, for exact or measured quantities, since we're within the metric system, both the 1 liter and the 1,000 milliliters are exact numbers, not subject to sig fig rules. So you would look at all your other values, your measured numbers, to determine your sig figs for the problem. For the second one, 1 hour equals 60 minutes. So therefore, you could have either the 1 hour in the numerator and the 60 minutes in the denominator, or the 60 minutes in the numerator, the 1 hour in the denominator. And it's your problem that's going to force one versus the other relationship there. And with them both being units of time that work for both the English and the metric systems, the 1 hour and the 60 minutes are both exact numbers. Finally, for that third learning check problem, 1 kilometer equals 1,000 meters. Just like the first example, we could have 1 meter equals 0.001 kilometers. That would be correct as well. But if we look at our options for this representation, 1 kilometer divided by 1,000 meters or 1,000 meters divided by 1 kilometer, either is an acceptable conversion factor, and yet again, the problem that you're working is going to determine which form you will use. Since they're within the metric system, they're also both exact numbers. Alright, so I keep talking about problems. Let's look at an example of a problem. And of course, the conversion factor that you're looking for is ordinarily obtained from the information in a word problem, or from some useful information that's provided with an exam, for instance, or from your text. If you are working a homework problem, of course you can use your text and look for the information there as well. But for this first example, the motorcycle was traveling at a speed of 85 kilometers per hour. Well, we could either say 1 hour over 85 kilometers, or we could say 85 kilometers over 1 hour, depending on what else the problem asks. For the second example, 1 tablet contains 500 milligrams of vitamin C. There we can get that equality from the problem itself, and therefore that 1, which is a counted number, an exact number, so 1 tablet over 500 milligrams of vitamin C, or depending on what the problem continues to ask, we could have the 500 milligrams vitamin C in the numerator and the 1 tablet in the denominator. Sometimes we'll even use percents as a factor, and this is oftentimes nice because we should have an idea of how a percent relates. If you've forgotten that, percent equals part over whole times 100%. Hopefully you heard that relationship back in middle school or high school, and hopefully it stuck because it's an important application of math in everyday life. If you're ever at the percent off sales, you should be able to figure out how much you're saving. I would never just walk up to the register and pay whatever they tell me, because oftentimes it's not correct, and typically it's that they're asking for too much money. So I always work my percents and make sure I'm paying what I should pay when I buy my sale items. So again, typically because we're talking about part and whole, we're talking about the same units. So there's not typically a separate unit if you're using the percent factor for most given problems. So the value of 100 is typically the whole, and so you could write it as 2 factors. If we see this example here, a food contains 18% by mass of fat, so 18 grams of fat per 100 grams of food, or we could say 100 grams of food per 18 grams of fat. Either way would work depending on the problem itself. But notice we have the same unit, although we're talking about something different. We're talking about either the grams of fat or the overall grams of food. So we don't just cancel those grams. We have to wait and see what the problem is really asking us to solve for. Another type of unit you might see from time to time, especially if you read any EPA reports, parts per million, ppm, or parts per billion, ppb, are often the ways that the EPA reports things. And again, it's not exactly what it sounds like. So it's not necessarily that you have 1 part of contaminant per million molecules of water, for instance. What it actually is the same as saying the number of milligrams per kilograms of substance. So milligrams of pollutant, for instance, per kilograms of water, if we're looking at a river or lake pollution, part per million value. Parts per billion is, again, not exactly what it sounds like. This time it's grams per kilogram, and that's why, since the previous one's milligrams and this one's now grams, we're off by a factor of 1,000 times, and that's how we go from million to billion for our parts per million versus parts per billion. If we look at our example, the maximum dose of lead in pottery glaze is 2 parts per million, so that means you can have 2 milligrams of lead or lead ion per 1 kilogram of glaze, or you could say in 1 kilogram of glaze, there's 2 milligrams of lead metal or lead ion permissible. So we can use the conversion factor and have either substance be in the numerator or the denominator. One place, in addition to those EPA reports that talk often about environmental concentrations, another place that you might see those values of ppm or ppb is in the toxicology reports. A measure of toxicity is the lethal dose 50, or the concentration of the substance that causes death in 50% of the test animals. So in those cases, the dose is typically measured either in parts per million, which would be milligrams of the toxic substance per kilogram of body mass, or parts per billion, you would have micrograms of the substance per kilogram of body mass. So in either case, we're looking at very small amounts, and therefore if you're looking at, say, a pharmaceutical that's been tested on animals, you want to have the dose that would obviously be therapeutic be much less than the LD50 dose, which is, again, potentially deadly to humans based on the animal model. So here we have table 1.12, and that brings us back to the very beginning of this chapter where I talked about Paracelsus and the idea of the dose makes the poison. In enough of an amount, anything can be toxic. So if we look here, table sugar, the LD50 there, parts per million value is 29,700. So that's a lot of table sugar for that poor little rat. But if you pump these rats full enough of anything, even something as relatively non-toxic as table sugar, in a large enough quantity, it's toxic. It can cause death. And we see a lot of the common household things. Boric acid you might use for ants or roaches because it affects their system, but it's pretty harmless to people. Baking soda, again, fairly harmless. Table salt, fairly harmless long term if you take in that much, or even just a little over the daily value of table salt, for instance. You might put yourself at higher risk for hypertension, but you'd have to consume a lot to have a lethal dose. As we go down, we start to see things that have much smaller values to give that LD50. And if we look at sodium cyanide, that's quite a lethal substance. Just 6 parts per million have the LD50 for those test rats. Okay, so let's go ahead and end this discussion with a final learning check. Look at each of those items below and write the equality and conversion factor, both types of conversion factor, switching the numerator and denominator. So for number 1, the meter and centimeter equality and conversion factors. Number 2, jewelry that contains 18% gold, the equality first, and then the 2 forms of the conversion factor. And then finally, 1 liter of gas is 95 cents. Again, that's a liter, not a gallon, so don't get too excited. But go ahead and write that equality first and then the 2 conversion factors. If you need a little extra time, please pause the video now. Otherwise, we'll take a look at how you did. Okay, so hopefully you had relatively little trouble writing these equalities and conversion factors. For number 1, 1 meter equals 100 centimeters, and that would have the meter in the numerator and the 100 centimeters in the denominator, or alternatively the 100 centimeters in the numerator and the 1 meter down in the denominator. And since they're based on conversions within the metric system, we expect the 1 meter and the 100 centimeters to be exact values. We look at number 2, 18 grams of gold equals 100 total grams of jewelry, and we could either have the 18 grams of gold in the numerator with the 100 grams of jewelry in the denominator, or vice versa. And then finally, we're expecting them both to be, we're expecting the 18 grams, because that was what we were provided, to be a measured value, but that would be in exactly 100 grams of sample. Finally, the 1 liter equals 95 cents, and we could have the 1 liter in the numerator and 95 cents down in the denominator, or we could have the 95 cents in the numerator and the 1 liter in the denominator, and we're expecting them both to be exact values in that last equality. So hopefully this is coming to you pretty easily. If not, as I've said before, please reach out, get in touch with me. Let's find out where you're having trouble and let's get it resolved, because this idea of conversion factors is a very important one that will follow you throughout the course.